Hi there. So here we're going to look at the practice of conducting an analysis of covariance. First of all, I'm going to import the data set on the bacillus scores of patients before and after treatment. So here's the text file. It's on my J drive. Here I am here, and what we have is the leprosy data. I'll open it here and import it. So here it is. So we've got a list of patients with three different types of drug. 10 patients were given one drug, another 10 a second, and 10 a third. And here is their bacillus score before treatment, and here is their bacillus score after treatment. So the first thing to do here is to plot the graph, and here we are running the graph, and here we can see that the bacillus score after does seem to be related to the bacillus score of the patients before treatment, although it's unclear whether the drug has any strong effect. Now, let's fit a model to understand this relationship. And to begin with, we're going to be fitting the classical, simple analysis of covariance model. So here what we have is the fit of a linear model with back after as our dependent variable, back before as our continuous predictor, and the type of treatment is treated as a factor. 1, 2 or 3 are not used as numbers but as categorical levels. After fitting the model, we can look at the breakdown in terms of an analysis of variance. And what we can see is that there's a highly significant effect of back before on back after, and yet there is no significant relationship between the treatment and back after once you control for back before. You'll remember that we are conducting by default a type 1 sum of squares, so we are controlling for back before as we should when looking at the effect of the treatment. Let's have a look at the coefficients that can be estimated from fitting the model. You'll see that we have an intercept here, we have a gradient for back before, and then we have adjustments for the different factors. You'll notice that factor 1, so the factor with level 1 is missing, and that's because it's subsumed within that coefficient for the intercept. That's the way the default contrasts have been set. Okay, let's move on and fit those lines to the data. So first of all, we can fit the first treatment, then the second, and the third to data simply by drawing lines with those estimated coefficients, and you'll notice that the fitted lines in these cases are all assumed to be parallel and that they have a common gradient of 0.8830. Now, just for completeness sake, I'd like to conduct a type 3 sum of squares. Of course, there's a number of ways to do this. We can change the order and simply look at the bottom listed predictor in each case, or we can actually call up the library car, which is what I'm doing, and then I'm calling up capital A ANOVA and setting the type 3 sum of squares within that for our individual model that we've just fitted, model 1. And here we come to very much the same conclusion. Now back before is investigated, but we're controlling at the same time and statistically eliminating the effect of the treatment when we're looking at back before, and likewise for treatment we're controlling for back before, and the conclusions are the same. Back before has a very strong influence on back after, so if you start with a high score, you typically ending with a high score too, but the treatment has no significant effect on the back after. Now let's actually draw out the residual plots just so that we can check the underlying assumptions of the fit of our GLM. And to do that, I'm actually going to plot, for simplicity, both of the individual graphs on the same point. So what I'm going to be doing is setting up a 1 row by 2 column matrix of plots using the par graphical command. Now I'm simply going to plot these graphs out. So there is the first, in which we examine the residuals with regard to homogeneity of variance, and there is the second, in which we examine the normality, and we can see that approximately these residuals do indeed tend to follow a normal distribution, and that the QQ plot is approximately a straight line. Now I'd like to go on and ask, what would the model look like if we actually fitted a model which had a gradient which could potentially differ for different levels of the treatment? You'll remember the classical Ankova assumes parallel lines such that the gradients are all the same, but it is possible to fit a more sophisticated model in which the gradients differ, potentially at least, between treatments. So here is this model here as we list it out. What we have here is back after is now going to be fitted with respect to not just the main effects, but also an interaction between back before and the treatment. By specifying the interaction, the default assumption is that the main effects, i.e. back before and the treatment, will also separately be considered. Now let's have a look at the analysis of variance for this second model. And this is what it looks like. Here there is no evidence of a significant interaction between back before and treatment, i.e. there is no evidence to reject the null hypothesis that the gradients of those relationships do not differ between the different levels of the treatment. There's also no evidence to reject the null hypothesis that the treatment has no effect on the back after score. And of course that is bearing in mind that using this type 1 sum of squares we are controlling for back before. And finally we see yet again a strong relationship on back before in influencing the back after. Let's have a look at the coefficients though, and here are the coefficients. You'll notice not only do we have a baseline gradient here, but with this interaction these different values will help shape the overall gradient according to the treatment level considered. Now let's simply plot out the overall graph again, but this time I'm actually going to be highlighting and fitting the models with different gradients rather than the same, and this is what it looks like here when we fit this model. The code for graphics is a little bit cumbersome, so it's perhaps easiest to view it directly from the web page. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.